I'm Darren Llewellyn. Welcome to this segment of MyToolboxTV. In this segment, I want to talk about three-phase motors, specifically induction motors. It's a very simple motor, and that's the reason it's used all over industry for any application you can imagine. It has very few moving parts inside, a couple bearings, and that's about it. We're going to talk today about the different components, the way it's built, and how to test those components. Let's take a closer look. Well, let's take apart a motor and see what's inside and what makes it so simple and makes this thing so popular in industry. If you pull the bell housing off, inside a three-phase induction motor, you'll find the rotor. Now, if you look inside, there's some windings on the periphery of the frame. Now, the squirrel cage rotor, as this is known, is the key to the whole deal. Because the way this is built is it's got stacked up metal, steel laminations right through here. Then it's put into a die-cast machine. And molten aluminum is injected into holes that look something like this. This is what the rotor laminations look like. They stack many of them up, then they inject aluminum into these holes. Now, we've took one and cut it in half. Here's a rotor section that's been cut in half, and you can see the metal laminations, but you can also see the shiny aluminum. Now, here's the way this thing works. If you look at the drawing, on the outside of a three-phase motor, there are coils on the periphery. Now, I've got them drawn very simply here, but they're a little more complicated, as you could see earlier. The way three-phase power works, the A coil would be turned on now, then shortly later, then the B coil, shortly later the C coil. Now, that makes a rotating magnetic field, the way this is happening. This magnetic field induces current into the aluminum bars that you see here. Current would be coming through like this, inducing the magnetic field would be inducing current into these aluminum bars. Now, we've gone one step further, and we took a rotor much like this one, and we soaked it in acid for a very long time. This acid melts away all of the steel but leaves the aluminum. And this is what is inside of that rotor. Now, this is why they call this a squirrel cage rotor. This is something that you ordinarily would never see in the field, because unless you soak your motor in acid for a very long time, which I don't recommend, you're not going to see this. So what happens is this rotor's in the center. This coil is turned on, a magnetic field induces current into these bars. Then that current in these bars creates its own magnetic field. And as that happens, this rotating magnetic field turns and causes the motor to turn. At which point, it induces magnetic field, induces current, and then this one switches to here. So we're inducing a magnetic field, or a magnetic field is hitting this rotor and inducing current into these aluminum bars, which creates its own magnetic field. That magnetic field follows the one that's rotating, and that's how it turns. A squirrel cage induction motor of this type has no brushes, has no centrifugal switch. It's very simple. You've got some bearings, and that's pretty much the only moving parts in it. The winding, which you see here, which you can tell looks like one continuous thing we've got drawn very simply here for explanations, has leads that are connected to these windings. And there's 9 connections on a standard three-phase induction motor. Now, we come back, let's talk about how we're going to test this thing to see if there's anything wrong with these windings. There's not much to test with the rotor. Not much can go wrong with that unless it melts or whatever. So there's not much electrical testing you can do there. But we can test the windings, and we'll do that next. Typically, a three-phase motor has 9 leads coming out of it. It can have a different amount depending on how it was manufactured, if it's European motor or not. Typically, those have 6. But the typical U.S. motor, induction motor, three-phase induction motor, will have 9 leads. Now, these leads are connected to coils. And if you look at the drawing, these coils are made in a pattern to where you can run this same motor for 480 volts or 240. And you simply change how you've got the 9 leads connected. And all the motors will have a connection chart on the side of the motor. Now what you're doing, let's for instance look at this as if we're going to connect this for 480 volts. Here are the coils, the way that they would be shown. The center connection here means that this is going to be a Y connected motor. They also have delta connected motors, but we'll look at a Y for simplicity right now. If you were to hook 4 and 7 together, 5 and 8 together, 6 and 9 together, and then run the number 1 terminal to L1, the number 2 terminal to L2, then the number 3 terminal to L3, you would be operating this three-phase motor. Now, what can happen with these motors is if they fail, sometimes they overheat, they get too much current through them, the insulation melts off, things like that. What can happen is one of these coils on this motor might be touching the case of the motor. It might be touching the case. And what we say then is it's got a ground fault. That would be that you got one of these 480 volt coils connected to ground. That would cause the fuse or circuit breaker protecting this circuit to trip, we would hope. Could cause additional problems as well. You may also have a situation where one of the coils has an open, where it's actually been broken in half by too much current, or could be a mechanical problem, cause the lead to actually break. So that would be considered an open. These will have different characteristics, cause different problems necessarily. Hopefully they'll both cause a circuit breaker overload to trip and shut down the circuit and allow you to come fix it. Now when we're going to test a circuit like this and test a motor, we can do your initial test with your multimeter, but when you really get down to it, you need to use a megger. If your multimeter will find the problem, you definitely got a problem. But for instance, if you use your multimeter to find a ground fault, your multimeter may not find something that a megger would find. The open, your multimeter is fine to find that in most cases. Now let's look in a little more detail on how to test these. Let's take a look at how to test a three-phase motor. I got a couple motors here. These are already connected, just like you saw on the drawing earlier, and so we just got 3 leads coming out. Now, a lot of times this test doesn't have to be done at the leads. It can be done at the bottom of the motor starter, as long as you make sure none of the control circuitry is involved and everything's turned off. It's safe to do it down here. Disconnects off, motor's disconnected. You can do a lot with motor testing with a multimeter. Put it on resistance scale. You've got the leads. There's 2 things you're going to be looking for, and that's ground faults and opens. You can also look for shorts, and let me show you how to do that. When you test between these leads, which are leads 1, 2, and 3, you're going to get some resistance measurement, hopefully. And this is 76.7. Well, let's check between another couple. We go to here, we get 76.7. Then when we go to here, which is the third combination, we get 76.7. What that tells me is that all of these windings are present. They're not opened. They're all the same. So what I measured, when I measured just now, I measured from here to here, and here to here, and from here to here. So I'm just making sure that all of these windings are intact, not open, and not shorted out. If they were shorted out, maybe this winding was shorted out to this winding, you'd get a different reading. You wouldn't get 3 that were all identical. Now I have no way of knowing if 76.7 is the correct reading for this particular motor, but I don't care, because it'd be odd if it wasn't, because I got it 3 times on 3 different ways of doing it. So I would be confident to know that this motor didn't have an open for sure, and it doesn't look like it's got any shorts. Now, another test that I would want to make is with a device called a megger, or a megometer. A megometer is a device much like the multimeter, where the multimeter uses a 9-volt battery, and that's the voltage you're using to test things with. This thing uses a high voltage, uses 1,000 volts. Also has a 500 volt range. When you use that higher voltage, you have a much better chance of finding a situation inside the motor. The multimeter can miss a lot of stuff that the megometer will find. The most important thing about the megometer is safety, because it is using a much higher voltage and it will hurt you. It can bite you. Follow all recommendations and instructions in your owner's manual for the megometer that you're using. Okay, less of a hazard with this as opposed to this. A couple things I want to point out. Another possible method of troubleshooting a three-phase motor is, let's say you're out in the field and out in the factory and someone says, hey, this motor's tripped out, so you got to figure out, well, is it a motor problem? Is it a circuit problem? Is it a conveyor belt problem? Is it a mechanical problem, not related to electrical? And maybe the problem is the motor starter is tripping out. Well, a way you can look at the motor to see if it's causing the motor starter to trip out is measure the current the motor is drawing using a clamp-on amp meter. And you can do that at the base of the motor starter. Is probably the easiest place to get that done. So check the current, and that would be the current right here on these leads here. If the current is, let's say the motor is supposed to draw 10 amps, but it's drawing 12 amps on all three legs, that's a mechanical problem or something outside. That's something causing the motor to do too much work. Because, yeah, it's pulling too much current, but equally throughout. Okay, so that tells me that's probably a mechanical overload of some kind. What if you check the current on all three legs and you get motor's supposed to pull 10 and you get 8, 10, and 15? Well, that's not a mechanical outside problem. That means you got a problem inside the motor, because nothing outside the motor, assuming your voltages are all level, is going to cause that internal issue with that motor. Okay, so just a quick thing that you can do is check the currents on all three legs to see if they're all equal. If they're all equal and high, motor overload. If they're all over the place, it's something internal to the motor. A short inside the motor, a ground fault, an open could cause that to happen. Another thing, easy thing to remember about three-phase motors, and one thing that's very simple about them, to reverse a three-phase motor, you simply reverse any two leads. So if you want it to go clockwise instead of counterclockwise, reverse L1 and L2, or L2 and L3, or any of them. Just reverse any two leads, and it'll reverse the direction. Well, hopefully you got a little extra out of three-phase motors today, the induction type anyway. And we're going to do more and more about different types of motors in the future. And so stay tuned, and we're going to be covering DC motors and other types of things, including VFDs and other acronyms as we go forward. Thanks for tuning in, and I'll see you next time.